All right, here it is. We talked a little bit about, excuse me, drawing Lewis structures before. We mentioned about, you can pair up the unpaired electrons and draw them out. That's fine, but it doesn't work for everything, and it's a little bit time consuming. So what I want to do is show us what are like my good method for drawing Lewis structures. Okay. Um, this is how I'd go through it. And we're going to think through this kind of like a flow chart as we go. Okay. And I'm going to work through some examples as we do this. And we're going to have a condensed down version of this, excuse me, as we try to practice some of this. And then this is a handout that you'll also have access to. So let's take a stab at some examples. All right. Well, okay, let's run through this. Our first step, we have to calculate our valence electrons because the valence electrons are in charge of the bonding. We're gonna draw a skeleton structure, so we have to decide two things. Well, we have to decide what the central atom is, and we have to connect everything together with single bonds. We'll add lone pairs to outer atoms and make sure that all the outer atoms have an octet. We'll look for electrons that are left over, and then we'll check for completeness, and then go from there. All right. Let's start this. Carbon tetrachloride. When we're doing these, okay. Okay, calculate valence electrons. Each carbon has got 4. Each chlorine has 7, and there's 4 of those. So I hate doing arithmetic in my head. There should be 32. Well, this will be embarrassing if it's not. Okay, draw the skeleton structure, carbon in the center. Right, we have to decide what the central atom is. Our official rule is the central atom is the least electronegative thing. Okay, which is usually the case. It's also usually the only one of its kind. So in this case, carbon is less, and it's also usually written first. So those three things are what's going to get us through there. Uh, Usually written first in the formula, usually the least electronegative, and usually the only one of its kind. Um, there we go. So if we have the carbon in the center, then all 4 chlorines are stuck on the carbon. Okay. You know what? I'm going to be proactive with figuring this out. 32 hours, right? Okay. So here we've used how many? We've used 8 valence electrons. Remember, each line counts for 2. You don't have to, I'm showing the work for the numbers over here. You don't ever have to do that for me, but if you want to do it for you, that's totally cool. This leaves us with 24 valence electrons left. So our step 3, add lone pairs to the outer atoms. 1, 2, 3, 4, 5, 6. Now that has 8. 2 for the bond, 3, 4, 5, 6, 7, 8. 2 for this bond, 3, 4, 5, 6, 7, 8. 2 for that bond, 1, 2, 3, 4, 5, 6, 7, 8. Okay. We put 6 on 4 different atoms. That's 24. So we got to 0. All right. Now, double check ourselves. Do we have any leftover electrons? No. That's good. Does our central atom have an octet? Yes. Do all the atoms have an octet? Yes. We don't have an ion, so we're good to go. Okay. It's not too terrible. We're going to do the same process for each thing as we go. Let's look at this. This is formaldehyde, CH2O. Let's see, the carbon's going to have 4. We're going to add to that 2 hydrogens, each with 1. And then oxygen has 6. So this is going to be 12 total. Okay. This is electrons. The atom in the center, again, least electronegative, usually written first, carbon. Okay. We have 3 things stuck to it, 2 hydrogens and an oxygen. So draw it however you feel like. I like symmetry. I also kind of know what the answer is going into it. So I'm going to draw it this way. Okay. We use 6 electrons. So that means we have 6 electrons left. Outer atoms need an octet. 2, 3, 4, 5, 6, and the bond makes 8. Okay. Oh, excuse me. Hydrogen's okay with 2, so this is good. Okay. So we did this, we did this, we did this. Okay. Add leftover electrons to the central atom. We don't have electrons left over. Does the central atom have a complete octet? No. Okay. Carbon needs to have 8 electrons. Remember, we said carbon likes to form 4 bonds. Carbon will almost always form 4 bonds. So we got to have 4 bonds in there. We don't have any more electrons to give to the carbon, but we need the carbon to have more electrons. So when that happens, we're going to form a double bond. And this happens by taking outer electrons away from the oxygen and sharing them again. There we go, with the carbon in the middle. So we have made a double bond in here. Okay. Things I want you to remember is that forming a multiple bond is hard. Well, I mean, it's easy to do on paper, but the atoms don't like to do it. Forming a multiple bond is a last resort. Okay. So only if the central atom doesn't have enough electrons and needs to have 8 electrons do you make multiple bonds. Okay. The biggest failing I see in Lewis structures is people will draw multiple bonds everywhere, and that looks bananas. It looks interesting and looks pretty or whatever sometimes, but it's not correct, right? You don't need multiple bonds all the time everywhere. Okay. Let's do another one. This is basically going to be all Lewis structures all the time for this one. All right, now we have a polyatomic ion. This is our ammonium ion. So nitrogen has 5 electrons. We have 4 hydrogens, each with 1. And then positive charge means we've lost an electron, so we're going to subtract 1. So this means we have 8 electrons. Okay. Hydrogen and fluorine are never the central atom, so this means nitrogen has to be the central atom. It's going to have 4 hydrogens stuck to it, like so. All right, that was 8 electrons. We have none left over. So, okay, we don't need to do that. Does the central atom have a complete octet? Yes, it does. Last thing, add brackets and charge for ions, and then we're done. So this has a positive charge, so we're going to need brackets and a positive charge to say that that is a polyatomic ion. Okay. Let's do SO2. Okay, all 3 of these things are in group 6. So we have 18 valence electrons to worry about. Okay, sulfur is less electronegative. We'll put it in the center. O over here. O over here. That gives us 4, which means we have 14 electrons left at this point. Give our outer atoms 12. 1, 2, 3, 4, 5, 6. Not 12, 8. What am I thinking? Okay, there's that. So we've used 12 electrons. That's what I was thinking. We have 2 electrons left over. So once we get here, now we're here. Okay, we add leftover electrons to the central atom. Whenever we do this, they have to be in a pair. All right, we're always going to pair things up. Okay, now we've used all of our, all of our electrons. And there we go. Does the central atom have a complete octet? No. Does sulfur need to have a complete octet? Yes. Right? Sulfur is big and needs to have 8 valence electrons. So we can, again, take outer electrons away from an oxygen and share them as a lone pair and share them in the center to make a double bond. Okay. All right. HCN. Okay. Hydrocyanic acid that we saw before. This is a molecule. We can draw its Lewis structure. Hydrogen is 1, carbon is 4, nitrogen is 5. So this is 10 electrons total. Okay. All right, we're gonna draw a skeleton structure. Okay, hydrogen can never be the central atom. Here, our central atom has to be carbon. Anytime we see something that's one each of 3 different things, a good shortcut to do is write them in the order of the formula. HCN. Okay, so we've used 4 electrons. Okay, that means we have 6 left over. Those 6 go on the outer atoms, so we're going to put them all on the nitrogen. Okay, -6, so 0, so we're done, right? We've added all lone pairs to the outer atoms. We don't have anything left over. Does the central atom have a complete octet? Not at this point. Carbon needs to have 4 bonds, so we're going to take a lone pair and share it to the middle. It still needs another one. We're gonna take another lone pair and share it to the middle. Now we get a triple bond. I'm gonna tell you a secret. It's not really a secret, but a shortcut if you want to think of it that way. Anytime you see something that has CN in it, it is most likely going to have a CN triple bond. And then it's bound to whatever the other thing is, right? BRCN, ICN, FCN if you're feeling disgustingly toxic, but there you go. Okay, the CN triple bond shows up a lot, so it's a good motif to remember. All right, HCN, about ALF3. All right, let's take a stab at this. Aluminum has 3 valence electrons. We have 3 fluorines, and each fluorine has, I don't need to write F. Each fluorine has 7. So that's 21, 22, 34 electrons. Okay. Fluorine is the most electronegative element. It's also never the center. I'm going to try to remember our nevers here. Hydrogen and fluorine are never in the center. So means aluminum is in the center. Okay. And we're going to have 3 fluorines stuck on the aluminum. There we go. Oops, I didn't draw the bond. All right. So that takes care of 6, which means we have 18 left over. 1, 2, oops. Come on, don't be sloppy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. And we hit 0. All right. Now we go through our checks. We don't have anything left over, so we don't need lone pairs on the central atom. Does our central atom have a complete octet? No, it doesn't. Okay, but now we have to think through this. Okay, remember, let me go back to the longer list here. Oops, there it is. All right, here we go. We are right here. No, but this atom is okay having less than 8 valence electrons because boron, beryllium, and aluminum are small, and they are perfectly fine having fewer electrons. I didn't write these in a good order. Beryllium is okay with 4 electrons. Boron and aluminum like to have 6 valence electrons. I will say this, boron and aluminum can have 8 if there are 8 valence electrons there. Okay. Also notice that these guys that are small, boron, beryllium, aluminum, and hydrogen and fluorine, don't ever form multiple bonds. So we don't want to draw multiple bonds to the aluminum from the fluorine. That's not going to happen. Okay. So aluminum is okay with 6. So this is good. We don't have to stress about it. Okay. Could we have ALF4 minus? Yes, we could, because aluminum can't have 8. Oh, I didn't plan ahead. Okay. AlCl4. Okay, I'm gonna erase this check mark and squeeze this other guy in here. Okay, same idea. We have one more. Remember, fluorine and chlorine are in the same group, so this is going to be 3. Sorry, 3 plus 4 times 7 plus 1. Okay, so what does that mean? That means 7 times 4 is 28. So this is 32 again. Okay. 32 electrons. I know. All right. Again, we'll put aluminum in the center because it's the least electronegative. Now aluminum has 4 things bound to it. Chlorine, 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 chlorine. I did not leave myself enough room. Feel free to fast forward through my crap. Aluminum, chlorine, 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 chlorine. There we go. Okay. That's 8, which means we're going to have 24 electrons left over. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, that's 24 electrons. We're down to 0. There's no electrons left over. Our central atom has a complete octet. Aluminum is fine to have 8 valence electrons. So we can go ahead and put our brackets and charge on here because this is a polyatomic ion. Okay. Don't forget the brackets and charge. I know it seems like it's really easy to do at the end, but you're going to be so excited that you got the Lewis structure finished that you'll just forget the brackets and the charge. All right, what do we got next? IBR5. Okay. So let's take a stab at this, IBR5. All of these are group 7, so we're going to have 6 atoms times 7 valence electrons. 6 times 7 is 42. Okay. All right. Guy in the center is iodine. Again, it's the only one of its kind. It's the least electronegative, and it is written first. Okay. The iodine gets 5 things stuck to it, so just kind of draw it out. Ends up looking kind of starfishy, but that's okay. Put some bromines on here. Okay, 1, 2, 3, 4, 5 bonds. So we've used 10 electrons. So this gives us 32 electrons left. And when we do that, that means we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay. Minus 30. So that means we have 2 electrons left over. Okay. If we have leftover electrons, they go on the central atom. So we're going to make a pair of electrons on the iodine in the center. Okay. So now we're at 0. Okay. Does the central atom have a complete octet? Well, I mean, kind of. It has at least 8. It actually has 12, right? Because we have 5 bonds and a lone pair. That's 6 things, 2 electrons each thing. That is 12 valence electrons. Okay. This is totally fine. Our idea here is atoms that are period 3 and bigger can have more than 8 electrons. Okay, because at this point, and we're going to get into this a little bit more too, at this point, the atoms are large enough to accommodate the extra electrons. Iodine's a pretty large atom as atoms go, and so it has no problem accommodating 12 valence electrons. Okay, let's look at ClF3 while we're on this one. Same idea. I have a hungry cat sitting here. Let's see, Cl. Oh wait, all these are in group 7, so we have 4 times 7 is 28 electrons. Okay, chlorine in the center because fluorine is the most electronegative. Slap 3 fluorines on here like so. Used 6. 28 minus 6 is 22. So then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, we used 18. That means we have 4 electrons left over. And we have electrons left over again, so they're going to go on the central atom as pairs. Just kind of put them in there wherever you can get them to fit. There we go. Keep them as pairs. That looks nice. Okay. Now this chlorine has 10 valence electrons. That's okay because chlorine is in period 3 or higher. Okay. What's next? Oh yeah, you can look at bigger things and draw bigger things. Okay, we just have to break things down. A lot of these bigger things are organic stuff, and so there's a lot of carbon in here. Remember, carbon likes to have 4 bonds to it, and so written in this shortcut form, we can actually just kind of mentally put the pieces together. Okay, so we have CH3, so we can draw a CH3. Carbon has to have 4 bonds. That 4th bond is to the next carbon over. This carbon is CH2. And then we have 3 bonds. We need 1 more bond. That looks like a double. Okay. And that's to an OH. Okay. Oxygen has 6 valence electrons. The picture needs 8. So we're going to give it a pair of pairs, 2 lone pairs. And that's ethanol. Okay. This organic stuff we can write in, you're not going to have to do a lot of it, but you can write it in chunks. One last one, acetic acid. We're going to write acetic acid like this. It's not very intuitive to draw the Lewis structure that way, but there are other ways to draw it. CH3CO2H, CH3COOH. Either one of these will give us a good Lewis structure picture, and they should give us the same picture. Okay, we have a CH3 again, so CH3 bound to the next thing over is a carbon. This carbon is bound to 2 oxygens, O, O, okay, and then the oxygen on the end is bound to a H, okay. Then we just have to fill in those extra electrons, and there we go. The carbon has to have a double bond to the oxygen because that's a central atom, right? If we do this in the order of Lewis structure things, we would draw like this, okay? Because those are the outer atoms. The outer atoms have 8, but we need to have this carbon have 8 as well. So we can share that inside to make a double bond, okay? Again, Lewis structures are going to come with practice. So the more you practice, the better you get at doing it, and the quicker you can do it too, because you're going to have to do a bunch of these on a test, and you don't want to run out of time. All right. I'll catch you later. Let me know if you have questions, and enjoy your day.